Hello, sir. Hello.
Hello.
Hello. Good evening, sir.
Good evening, Narendra.
Yeah.
So yeah, it's I think 6:05. We can start.
Okay.
Last time Abhik took the class right on Friday. Hello, Narendra.
Hello, sir. Actually, I missed that class. I was in a busy somewhere. That is the
Okay,
class I miss throughout the session. That is
but it
only the class.
but it happened right. It happened, na?
O- Okay, I can see from screen
Okay,
what matter sir has taken. I will collect, no doubt.
okay. So anyway, we'll start. So basically, last like this week 9 in that course videos, you can see it is mostly it was related to entropy interactions for uh, you can say uh, control volume systems, so like heat exchanger, turbine, pump, uh, yeah, so that type of discussion was there. So basically, like, if you want to simplify this analogy in your head, because the thing is, in class you study first law then second law, and first law for control mass system, control volume system, then second law for control mass and control volume. But in reality, when you solve the problems towards the end of the course, so it's like they will ask you everything. You will have to apply first law, second law, and in future availability and all those things are also uh, will be required. So what I think is better approach is uh, you study control mass system and all the aspects, whatever have been taught so far, and then take control volume systems, and then study all the aspects. So basically, what I mean is, you can write this first law for control volume system as we'll take this uniform state, uniform flow system process. So in that case, we have seen this earlier. We can write Q plus Mi Hi plus Vi square by 2 plus Gzi equal to Me He square by 2 plus Gze plus the work done by control volume. And there will be this term which will be because of unsteadiness of the system. So here keep in mind that you cannot write enthalpy. Here you have to write internal energy, this U2 and U1. So this is for unsteady and sorry, unsteady and uniform flow. Uh, Not unsteady. I mean it's like uniform state, uniform flow. So basically, there is a temporal variation, but there is not a spatial variation in your control volume. Uh, and if you apply it for steady state, steady flow, I mean steady state, steady flow, uh, control volume, then you can write this M2 and M1 term will go. So essentially, it will be, and here it will be in terms of time. Like uh, in the first equation, you do the time integral, so you get the values in joules. Here it will be in watts. So the brackets remain same, and here it will be exiting m dot He plus Ve square by 2 plus Gze and work done by the control volume. W dot. So one thing to keep in mind is these equation, the first uniform state, uniform flow, it is in the unit of the equation is in joule energy unit, whereas the steady state steady flow equation has the unit of power. So work done per unit time, joule per second basically. Now the reason why I've written this is you can here only you can write the entropy balance or entropy equation, and that way it will be easier for you to remember. So if like I'll just write second law. I mean, this is not a hard and fast language, but just to be like concise in this manner I'm writing. If this type of system is there, uniform state, uniform flow. So basically what happens in this case, uh, you are basically writing entropy balance. So uh, I hope you remember in class professor has described it, derived it like from Reynolds transport theorem, and there we have capital N, small n. So in capital N you put the total entropy of the control volume. In small n you put small s, that is a specific entropy, and then depending on the steady or uniform state flow process, you take that capital ds by d capital S by dt of control volume. That term goes to zero if it is a steady process. If not, you do the time integral over certain uniform states. So 2 and 1 subscripts are used for that. So if you write that way, and your total entropy generation will be comprising of Q by T, and there will be entropy generation term, source of entropy generation, and there will be MESE minus MISI. This will be for this will be across the system boundaries wherever exit and inlets are there, plus that term where you do the time integral over two uniform states 2 and 1, so that will be M2 S2 minus M1 S1. And here this Q by T, summation of Q by T, so wherever the heat interaction is taking place at interface between system and surrounding, at that interface only you have to take the temperature, and depending on the sign convention you will sum up the uh, Q by T values. Accordingly the sign will come accordingly. If it is heat is provided to the system, it will be plus, if not minus. So this will be for uh, uniform state, uniform flow, and for steady state, steady flow, you can again write it as uh, 1 second. You can write this Q will be now time, function of time. So entropy generation also within the control volume will also be a function of time. Then m dot E SE minus m dot I SI. So here the equation simplifies, and since this is a steady state flow, and you have to take that integral basically. 1 second, let me just see. Am I making any mistake or something? Uh, 1 second. Yeah, so it is okay. In steady state, you have this summation sign, but in uniform state, uniform flow, anyway, you are doing integral, so you can write that sign and be done with it. But anyway, the point is, if you write this type of equations in one place, that is good for you, because by this time, some of you might have forgotten about the first law, and when you solve some problems in this discussion, you'll realize that you cannot solve the problem using only second law, or you cannot do it using only first law. So you need both of them. So that's why I've written it down here. Apart from this, in the last week's classes, one important thing was there, that A reversible process can be represented by combination of reversible adiabatic and reversible isothermal processes. So based on that only professor derived this work done for control volume as minus VDP. This V is a specific volume from inlet to exit. So you can follow Professor Suman sir's lectures and understand this point that reversible process can be described as a combination of reversible adiabatic and reversible isothermal process. And if you want more deliberation on this, I think in PKNAG you can find. I think it's like initially only it's there. They will draw a cyclic process, then they'll take the slices of that circular process, and each slice will be so small that reversible process we can be represented by a horizontal line and a vertical line. So the horizontal line on TS plot represents isothermal process, and vertical line on TS plot represents isentropic process, which is reversible adiabatic. So I mean, you can go to PKNAG and see it is, I think, very initially only it is there when you start describing some process and all. So they'll take something, some cyclic process like this. Sorry, some cyclic process like this on TS plot, and what they will do is they'll divide this process into number of cycles like that they mention, and in the end when you add up, the vertical lines will cross and only these horizontal lines. So if you zoom out on this area, you take in a infinitesimally small slices, so this variation will be not visible to naked eye, but if you zoom out, it may look something like this. So if you take one slice, you can represent this process using these two lines. So basically, if you're going this way, 1 to 2, you can represent 1 to A and 1 A to 2. So this will be constant temperature process. This will be constant entropy process. So basically, you can represent reversible process with combination of these two. So that was the point, and this important derivation comes out of that. You'll use this VDP work done for pump, maybe turbine if you know the specific volume variation with respect to pressure. But generally for turbine we use enthalpy because those data are available conveniently. And for pump, anyway, the work done is not that much because we handle liquids in pump. So specific volume change is almost constant. So that's why we take small v to be constant in this expression, and we take it out of the integral sign, and we just do the delta p integration, which is dp integration, which is delta p. So that's why for pump it is pump it is easy, but for turbine it may not be that easy, that integration. So that's why we rely on enthalpy values. So that is one point. Then I think there was one last bit was about the conservation of mechanical energy. This relation also you might have seen. I will not deliberate more here because you in maybe in fluid mechanics and all you'll see this in depth. I mean, Suman sir's lectures on YouTube are also very good for if you want to study fluid mechanics. I don't know for BTech how much of that will be relevant, but even in case of PhD also people follow Suman sir's lecture on NPTEL YouTube. They are freely available for fluid mechanics. There you can deliver details. You can find details about this there. But only one part that I want to highlight is this is the equation that was derived in the class is for mechanical energy, and it comprises of kinetic energy, potential energy, and I think they call it flow energy or something, flow work. Those three parts are here. Keep in mind that temperature effects are not here. Uh, Temperature effects are considered in internal energy. So that's why when you wrote first law, you wrote E as U plus KE plus PE. This is for closed system. For open system, there will be flow work also. So this U is a function of temperature basically. Temperature changes are accounted in U, and mechanical changes are accounted in this form. That's why they are called as mechanical energy. So since you are a mechanical, you're a student of mechanical disciple, you should at least know this. So anyway, I think that's the crux of theory, and then we'll go to problems. Uh, I'll start with a simple problem. Maybe you might have seen such problems in your class or somewhere else. But today I thought I'll take some problems from previous GATE or ESE exams. So there is one problem. It is a. I'll give you the data. Uh, there is a intersection of two pipes. So basically, there is a device like this. So you can see this anywhere in your home. One. So basically, there are two inlets to this system. Two. And these fluids mix, and finally they come out at 3. So this is the water. So I mean, I just write it here. This is water, and this first stream mass flow rate. 1 second, it is in. You can take mass flow rate as m dot 1 as 4 kg per second, and temperature of that flow stream is 40 degrees Celsius. For second stream, which is also inlet, m dot 2 is 6 kg per second, and temperature is 100 degrees Celsius. I know some of you may see and say that water will boil at 100 degrees Celsius, but for this discussion, don't go there. Just follow the data. It was given. And this is a subjective question from ESE exam 2005. So it is a 10 mark question in that exam. I think 200 marks exam or 300 marks exams was there. 2 papers. So one of the paper was, I think paper 1 was thermodynamics. There they used to ask such questions. And believe me, slight modification of this question, maybe I'll take that also. That will be for 20 marks. So this is not that trivial question. So please, I mean, if you can solve these type of questions, that means you are in a good shape. So this is the given information, and to find, you need to find. First part is temperature of stream 3. So basically exit temperature, and you need to find change in entropy of this system. So these two are there. So basically first you define your control volume. So to do that, let me just highlight it with different color. You take this whole system as your control volume, and then you start solving the problem. So basically, and this is a steady process. So this is a steady state. I mean, the system has achieved a steady state. So Now, I think some of you have already figured out the first part is easy. You need to apply first law. So for first part, you'll do apply energy balance or first law. You can write both the ways to control volume. So basically, since it's a steady state process, your m dot I will be equal to m dot E. Here m dot I is m1 plus m2. That will be equal to m2, m3, m dot 3. So basically it will be 4 plus 6, 10 kg per second. And now and this system is adiabatic. You can take that thing also. Uh, let's make it simpler basically. Uh, if it is not adiabatic, you can just write, depending on the size of heat loss, you can take that term in the first law. So basically, uh, this is actually a mass balance. I mean, I have written energy balance. So don't get confused because eventually you have to write energy balance. Energy balance will be something like m dot 1 h1. You are neglecting kinetic energy and potential energy changes. So basically, whatever I told you, these assumptions also you need to write if you are writing a subjective paper. But here we are targeting maybe GATE exam, like optional, sorry, MCQ type questions. There, I am just telling you the assumptions. But when you appear for any subjective paper, you need to write everything. You can't just do this hand wavingly. But anyway, that's not the point of this discussion. But you should keep that in mind. And M3, H3. If there is some heat loss, you can just add some Q here. So don't worry about that. In this question, there was no heat loss, so your life was easier again. So, and now since it's a water, you can write H as Ct. So basically, you can write Cp or C 4.18, and that will get cancelled on both sides. So basically, your T3 will be. I'm skipping one step here, but I hope you can understand that. Divided by m dot 3. So now uh, you know m dot 1, m dot 2, m dot 3. You know T1, T2 also. Do the calculation and you should get T3 as uh, it should be around 1 second. I have the answer in Kelvin, but anyway, 4 into 40, 160 plus 6 into 100, 600 divided by 10. So 76 degrees Celsius. Uh, so this should be your first answer. Now the second part, change in entropy. Here, since there is no heat transfer, heat loss to the surroundings, you can neglect that Q by T term, and you can write the entropy equation again. So basically, what you do is hmm, you can I'll just write the equation. I'll not skip this one since it's the first question itself. So basically, here is only like there is no Q, but still I'll write Q dot T plus S dot gen equal to summation m dot E S E minus m dot I S I. This is your general typical equation, right? There is summation sign also, but here it will go to 0 because it's an adiabatic control volume. So here itself you can write what is the entropy generated as S dot gen. M dot E is basically m dot 3 S3 minus m dot 1 S1 minus m dot 2 S2, and m dot 3 is a summation of m dot 1 and m dot 2. So basically m dot 1 into S3 minus S1 plus m dot 2 into S3 minus S2. I hope this part is clear. You are just doing rearrangement of terms. And now, what to do next? Because you don't have any this thing. You don't have a steam table or any data given in the system in the question, right? So here, you know that for that MCP ln T2 by T1, if it is ideal gas, there is one additional term, maybe pressure or volume term. But this is water, so that term is going to 0. So here you can just write m dot 1 into ln. Uh, there will be Cp here, m dot 1 into ln T3 by T1. Let me put actually m dot 1 Cp ln T3 by T1 plus m dot 2 Cp ln T2 by T3 by T2. I think you can solve this, but a very important thing to consider here is this T is in Kelvin. First part we solve it as degree Celsius because there it doesn't matter. It's it won't change basically because you'll just do constant addition on both sides. So that will be fine. But here you need to remember this thing. This is the very casual mistake that you can do. And if you do these calculations by taking Cp as 4.186 kilojoule per kg Kelvin, you'll get the first term as 1.82 minus 1.66. So basically 0.16 kilojoule per Kelvin. Uh, so yeah, but I think the unit should be m dot is kg per second. ln does not have any unit. Cp is kilojoule per kg Kelvin. So there will be 1 second also. So basically this joule will become watt because m dot has a per second, right? So keep in mind that units also. So this should be your answer. So this is a simple question that you may face. Uh, now I think I initially also I said there is one type of question,
Sir,
you know.
hello, sir.
Bolo.
Sir, I have just any doubt in the last
Hmm.
question. Sir,
Bolo, bolo.
this is for the gas, yeah, steam.
Water, liquid water.
If it is a water, sir, then in this energy balance equation, can
Hmm.
you write like this T3?
Why
Because
can't I?
if it is a water, enthalpy H1, we cannot you'll get from the temperature given.
Hmm?
H1 enthalpy,
Hmm?
it is a Cp into the T1. So
Hmm?
that is, I think, formula for the gas.
No. How else will you calculate enthalpy for water here? I'm just
You can, the
counter question.
temperature is given, sir.
Uh,
Temperature is given.
okay. Then
Though state is not defined completely, but suppose the temperature suppose is given, and if assume suppose the saturated water, then we may get a enthalpy.
see if you have table, then you can do that way. But in this question or in this exam, table is not allowed, and data is also not given. So that's why the CPT assumption you can make. I mean you can check with the steam table also. Eventually you should get the same answer because whatever factor you whatever function you use for enthalpy to relate it to temperature, that will be same for on both sides, right? On LHS also it will be same function, on RHS also it will be same. So
Oh,
basically in the end you'll get the same value because it is a weighted average, weighted sum divided by total. So uh, I mean I get your point. You can try this that way also, but I think
okay,
you will end up here only because
okay,
it will get cancelled on both sides, right? Numerator, denominator
okay,
also.
okay.
So Yeah. So anyway,
Okay.
moving
Okay.
on. So
Okay. Thank you, sir.
okay. So yeah, there is one more type of question generally which is asked is uh, this is like this comes in this inventor's claim. So basically, they'll give you one device, and they'll say that this is invented by some inventor, and that inventor is claiming that this device is feasible and it is giving efficiency greater than Carnot cycle or something like that. So you need to verify whether this device is in reality it is uh, it is feasible device or whether it is imaginary construct. So that type of questions are there. We'll take one example here. This is also previous year ESE question only. So basically, and that the format for these questions are also similar. You'll have such certain device. They won't tell you what is in the device. They'll just say that there is one device in which air is coming. Air is coming at temperature of 21 degrees Celsius, pressure of 5.2 bar, and mass flow rate is not given. That is unknown. And they'll say that this device gives output in terms of two air streams, so 2 and 3. For M2, the temperature for the second stream, the temperature T2 is 81 degrees Celsius, pressure is 1 bar, and mass flow rate is 40% of M1. So whatever was coming in total, out of that 40% is coming out here. And then there is information regarding the third stream. There is T3 equal to minus 19 degrees Celsius, P3 equal to 1 bar, and M3 no need to tell, but it is a 60% of M1. This is a steady state device. Generally, it is a steady state. So basically, what the inventor is claiming is that you supply air at atmospheric temperature but higher pressure, and as an outlet, you'll get one stream which will be hot but at a slightly lower pressure, and the other steam will be cold and at a slightly lower pressure than the inlet. So basically, this is a typical setup that is there for these type of questions. So I thought I'll take one problem like this also. So you don't need to know what is inside this device because this is thermodynamics course. Maybe in some other courses, the discussion will be relevant for that. What is the inside of that? If this device is feasible, then only it makes sense to go inside the device. If it is not, then there is no need, right? So first, we have to verify that you know whether this device is feasible or not. So uh, to do that, first we'll divide our attention to defining the control volume. Generally, you take the whole device also, and if there are some inlet outlet pipes, they also you consider in the control volume so that there is no complication. Then you come to the solving. So basically, the structure is same only. First, you apply for first law of thermodynamics, energy balance. If it satisfies that, then you go for entropy balance. And if it is satisfying that also, then the device is feasible. I mean, the governing equations are satisfied and it's a practically feasible device. So now again, so uh, the given in like additional information is there is no work done by control volume. It's there is not a there is no work done to the control volume or from the control volume. It's an adiabatic device, so heat loss is zero or heat gain is zero. Changes in kinetic energy and potential energy are neglected. I mean, this is given in the question itself. You don't need to make these assumptions. And in question itself, it is given that assume air as an ideal gas. So this also makes your life easier. So these additional informations are given in the question itself. Uh, so now you have to find feasibility of such a device, whether this claim is valid or fake. To do that, you need to have you need this device to satisfy first law, which is energy balance. Essentially, it's energy balance here, and second law. So basically, the SGen term, entropy generation term, should be greater than equal to 0. Equal to in case it is reversible, or if it is not mentioned somewhere, you can just take greater than 0 also, but more apt description should be greater than equal to 0. So if it satisfies these two things, then it is okay. So now first energy balance, it is easy to verify. It will be similar to what we did in the last question, that m dot 1 m dot 1 second, m dot 1 h1 plus m dot 2 h2 should be equal to m dot 3 h3. So you take left hand side and 1 second, I think it should be 2 plus 3. Yeah. So subscripts will change in this problem. That's so basically 2, 3 are your exit streams and 1 is your inlet. So it will be this way. So you take LHS and let us assume, let's say m dot 1 is equal to 1. This will make our life easy. There is no, I mean, like you may get confused. You can take it as some variable m also, but just to uh, like make this anyway. Let's let's not go there. Let's take it as m. Maybe some of you might get confused. So let it be m. It will be just constant multiplied everywhere. But this mass flow rate value, uh, it becomes important. Maybe in the entropy calculation I'll tell you, but there also it should not matter. Anyway, so let's move on. LHS is this term. So m dot 3 h3. Basically m dot 3 is 60% of m1. So basically 0.6 m. And now here you can take Cp T. Here also T you can take in degree Celsius, Kelvin doesn't matter, but let's take in Kelvin only because otherwise there is a confusion here. So 21 is 273 plus 20. 1 second, this is m3. So it is minus 19. So this is minus 19 plus 0.4 m into Cp into 273 plus 81, I think. M2 is 81. Yes. So one question can be, the pressures are different, right? Pressure is 1 bar here, and initially pressure is 5.2 bar. So can we take Cp? But because we are assuming air as an ideal gas, its Cp is function of temperature only. So the pressure effect is not coming into the picture here. So anyway, so this thing will become, I think it will be like mCp into some value. So that should be around, it should be 0.6 into 273 minus 19. That is 254 plus 0.4 into 453. So this will be, this is 152.4 and 0.6 in sorry, 0.4 into 354. This is 141.6. So if you add this, you should get MCP into 294. Then go for RHS. RHS is basically, I mean, this is m dot everywhere. But anyway, you can write it anyway, that is fine. But make sure that you know that unit is in kg per second. Don't get confused there. Okay, so M1 is total M, 100%. CP into T1, 273 plus 21. So this is MCP 294. So basically, since LHS is equal to RHS, first law is satisfied. So 50% of the work is done. Now check for the second law, entropy balance. Basically, entropy balance equation you can mention. So here there is no Q term, so that summation Q by T will go to 0. So directly Sgen will be m dot exit m dot S3 m3 S3 minus plus m2 S2 minus m dot 1 S1. I hope it is correct. I mean, I hope you get the point. Then again, now the thing is m dot 1 is equal to m dot 2 plus m dot 3 since it's a steady state. So there, then this equation again becomes S3 minus S1 plus m dot 2 S2 minus S1. And again you apply that since it's an ideal gas, Cp ln T2 by T1 minus R ln P2 by P1, and similarly for the second bracket m dot terms. So you have temperature, you have pressure. Make sure that you enter the temperature in Kelvin. So if you do all these precautions carefully, I'm not going into the numerical part. Maybe because if you do that, it will take some more time. So it will be a good practice if you can do it on your own. If not, I'll just give you the answer. So the first term will be 0.264 and the second term will be 0.196. So essentially the total will be 0.459 and this will be S dot gen by M because M is unknown, so we take it on the LHS and the unit will change. So basically it should be, this thing CP is kilojoule per kg Kelvin, and we are taking this S gen by M, so it should be per mass basis, kilojoule per kg Kelvin only. So the unit is finally kilojoule per kg Kelvin. I hope this is correct because see this M is in kg second, this S dot also has second, so that gets cancelled. So in the final answer there will be no time value here, no time unit. So basically it should be kilojoule per kg Kelvin. So now this value is greater than 0. So therefore the inventor's claim is valid and such a device is possible according to thermodynamics. But now the next part of the investigation will be what is inside this device. So that is not in the scope of this discussion, but I'm just telling you how it goes. So this type of questions are also very common in this field, in this type of in this area of thermodynamics. Other than that, let me just see if any. By the way, this question, this entropy, this device inventor's claim, this has been asked multiple times in like civil services, uh, engineering services. GATE also, actually GATE is a MCQ exam, so there may be, but I think this enthalpy balance, this type of questions are asked in GATE also, 1 mark. sometimes 2 mark. So this is important, is what I'm trying to say. Other than this, let me just see if I find any good question. If not, we'll go to some other questions. Just, but please make sure that you understand these type of questions. These are important. Uh, hmm. We'll take one more question from like similar question to what you may see in your assignments. Uh, let's see. Actually, I am trying to avoid these questions because Abhik is also taking them. So if I take the same question, there is not much that I can do also. So anyway, but this is what it is. There is this question. I'll give you the data. It's a two-part question. There is there is a compressor. I mean, by this time, I think you have understood that generally you draw a compressor this way, and you know if you want to draw turbine, this is your compressor. If you want to draw turbine, you draw this way. So your inlet will be here in this case. So this is a typical convention that is followed. I mean, you should by now you should have caught this. So anyway, in this question it is a compressor, and after compressor there is a heat exchanger which is called as cooler here. So basically what happens when you compress the fluid, its pressure and temperature both increases, but for the end application you need higher pressure. You don't want higher temperature. So that's why you cool it. So the temperature comes down, but the pressure is still high. And then you supply this air for a desired application. So this is your third part. Here, heat is rejected. Then since it's a turbine, it's a compressor, you have to give some work input to the compressor. And this is air. The working fluid is air. So now the data given is m dot of air is 0.5 kg per second. And at the outlet, you need P3. I mean, the air at the outlet, it should be at least at 500 kilopascal, and T3 maximum is 30 degrees Celsius. So it should not be more than that. Whereas local temperatures, I mean ambient temperature and pressure is, we'll use T0 for ambient, is 20 degrees Celsius, and P0 is 1 bar, so 100 kilopascal. So these are the things given. And one more assumption is, it is mentioned in the question itself that assume compressor is reversible. This is a very important assumption because if it is not mentioned, you cannot assume it. I mean, sometimes if it is not mentioned that air is an ideal gas, you can assume it because it's a reasonable approximation or assumption. But assuming compressor or turbine to be reversible, it's not that great of approximation. So you should not do it on your own. So if you sometimes if you can't solve the question, don't take this assumption and solve the question. That will be wrong. So anyway, so now, but in this question it is mentioned itself here, so you can go ahead and take it. And now you have to find what is T2, temperature of air exiting the compressor. And the next part is you need to find, this is the first ask. Second is power for compressor. So basically, how much work done. I should not write work done. I'll just say power. power requirement for compressor. This C is a compressor. Okay. So now it is not mentioned, but you can assume the air is supplied at this ambient temperature and pressure. So this will be your T1, T0, and P1 will be P0. This is a reasonable approximation, but this is an important approximation which should be given. So first part is now here you have, you know, see in cooler, you know, the temperature comes down, but the pressure more or less remains same unless and until pressure drop is mentioned. So basically, P3 is equal to P2, and P3 was given as 500 kilopascal. So P2 is also same, and in the inlet, you know, P1, which is ambient pressure. So you know, like for the compressor, you know P1 and P2. You know T1, but the T2 is unknown, which is asked. So here you can assume air to be an ideal gas, and it is mentioned that the compressor is reversible. So and there is not like mention of heat loss is also not there. So you can assume this is adiabatic also. So it is a reversible adiabatic. So basically it's an isentropic compression. So air is an ideal gas undergoing isentropic compression. So you know, so for adiabatic like reversible adiabatic process, you can use this like for ideal gas you have PV equal to RT, right? And for adiabatic process, reversible adiabatic, you have PV gamma equal to C, and gamma is Cp by Cv, which is 1.4 for air. Generally for diatomic gases, it is 1.4. So you have these two equations, and you need a final expression, which will be, giving you pressure as a function of temperature or vice versa. Because here is no, like, you don't want to deal in volume, because when you do the compression or expansion in turbine, volume continuously changes, and it's better to deal in pressure and temperature. So now how will you go about it? So you, like, some of you might already know this, but you need to basically eliminate V from this equation, and this is I mean, you can do the simple exercise like this. So basically from here you can write V as RT by P and put this here. So therefore you will get P into RT by P power gamma equal to C. So R is a constant, so that will also go into this C. So essentially you'll end up with P1 minus gamma into T to the power gamma equal to C. So basically your T will be C divided by P to the power 1 minus gamma, and whole thing raised to 1 by gamma, because we have T to the power gamma here. So this is what we generally use. So basically you can further simplify this. This C to the power 1 by gamma is anyway constant, so you can just write it this way. And 1 by P, 1 minus R is in the denominator, so when it goes to the numerator, it is gamma minus 1 and whole power 1 by gamma. So basically K into gamma minus, like write it like T2 by T1 is P2 by P1 power gamma minus gamma. So this from here, like simple ideal gas equation and adiabatic control compression, adiabatic process formula, you can derive this thing. Maybe like in exam, if you forget, you can derive easily, no issues. So now just plug in the values. T1 is at, I think, 20 degrees Celsius. Yeah, T1 is 20 degrees Celsius. So, like, it depends in which unit you want the answer. If you want T2 in degrees Celsius, keep T1 also in degrees Celsius. P2 is 500, which is P3. P1 is 100. So for air, it will be 0.4 by 1.4. So if you do this calculation, uh, this 0.4 is basically 2 by 7, right? So, 1 second, 2 divided by 7. This is 0.286. So 5 raised to 5 raised to
But temperature should be
0.286.
in Kelvin.
Tell me.
Temperature should be in Kelvin.
Ah, yeah, yeah. Actually, I mean, since it's a ratio, it should be. You're correct only. My bad. Uh, yeah, it should be 293. Thank you. This was a mistake. By doing this first law of balance, I got carried away maybe. So anyway, so if you do that, the final answer you should be getting around 464 Kelvin. This is the answer for first part. Second part is you know uh, you need to find the work done required. So basically, you can write first law for compressor, and I think there is no heat transfer. So basically, work done will be m dot h1 minus h2, right? Because uh, it should come negative. Yeah, so this way it will come negative, h1 minus h2. So basically, h you can write CPT, and you don't have mass, you have mass flow rate also 0.5 kg per second. So this value should come as minus 85.75. It is minus because we have to give the work to the system or the control volume. So this actually one more part for the question is there. So you need to find this heat rejected from the cooler also. But again, this is again the you know again the energy balance only. What I would have given more to this question is entropy balance. So basically, uh, you know, uh, since this compressor is reversible, this S dot gen term will be 0. Since this Q dot from the compressor is also 0, since it's a adiabatic compression, that summation Q dot by T term will also go to 0. So basically, your S2 equal to S1, that will be there. Uh, because mass flow rate is also same, so basically S2 is equal to S1. And in cooler, you need to apply the second law. So there you will use that formula. Uh, Here Q rejection is not equal to 0, right? So Q by T will be there, and T will be T0 because it is rejecting to the heat at 20 degrees Celsius. And we assume that the delta T is not much between cooler surface and the ambient. So you can take T2 as T0 as 220 degrees Celsius. So that will be your LHS. SGen will be there since it is not mentioned that cooler is a reversible device, and that will be equal to m dot S3 minus m dot S2, and then you can do that CPL and CPL and T 3 by T2 minus R uh, ln P3 by P2. So from there you will get the RHS, and you have Q by T on the LHS. So you take that on the RHS. So basically SGen you will get, and that should be positive. Uh, I was expecting this will be asked in this question, but it is not. So anyway, but I hope you understood what I have explained just now. If not, you can let me know. You can take this as an exercise to calculate the entropy of this thing. Uh, Here again. one more question is there, but yeah, we'll take one more question because we started 10 minutes late. So we'll take one more question here. Actually, I feel, some assignment questions are easy and that won't help you much going forward. So what you can do, you can go through previous year GATE or ESE questions, whichever exam you are targeting for, or any standard textbook also. You try to solve there. If you face any problem, maybe you can tell me that problem number or something so that we can also discuss. Anyway, but coming back to this discussion, we'll take this last question and we'll stop today. So there is a heat exchanger. It's a two-stream heat exchanger counterflow. I hope you know counterflow, parallel flow. Some sort of heat transfer you might have studied till now. So counterflow is one stream will be in the plus horizontal direction, then the second will be in the minus horizontal. So this is the first stream, this is the second stream, and it's an indirect heat transfer. So basically these two air streams are not mixing, they are flowing through tubes, and these tubes are by some mechanism doing the heat transfer. So m dot 1 is 2 kg per second. 1 second. So basically m dot 1 is 2 kg per second. P1 at the inlet is 125 kilopascal. T1 at the inlet is 1000 Kelvin, and P1 at the outlet is 100 kilopascal, and T1 at the outlet is 400 Kelvin. So basically this is the hot stream that is losing the heat to the cold stream, and the working fluid is air. Both are air only. Oh no, the second one is water. So this guy, the m dot 2 is 0.5 kg per second. It's water, liquid water, and it is entering at 200 kilopascal. It's a forced convection, and inlet temperature is 20 degrees Celsius. We'll write everything in Kelvin only, just to avoid that mistake which I did some time back. And it is leaving at same pressure, so there is no much pressure drop in this stream, second stream. So what I'll do, instead of writing this m dot p1 in, p1 out and all, we can just write the exit as 3 and this inlet as 4. So basically this will simplify our notation. So this is essentially P1, this is T1, this is P3, this is T3. Here in is P4, T2 in is T4, and P2 out. So basically P2. So sorry for making this confusion about the symbols, but I have given as 1, 2, 3, 4. You can do it your own way, doesn't matter. One more thing is this heat exchanger is adiabatic. I think so. 1 second, I'll check. But yeah, it is adiabatic. Yeah, so now you need to find what is the temperature of exit temperature of water. So that will be T2 by this diagram. I mean, I'll just write it here only. This is air and this is water. Second part is, I think, entropy generation. Total rate of entropy generation. This will be Sgen. And yeah, this is the question. So now this is a steady state process. So whenever nothing is mentioned, you can assume it as a steady state process. So by that logic, I'll now start with the first law. Apply first law to control volume. And what is your control volume? Your control volume is the whole heat exchanger. This is an important step actually. Many times we forget to define the control volume because we understand that this will be the control volume, but if it's a subjective question, if you don't do that, you'll lose marks. So anyway, now first law, there is no heat loss, there is no work done also. So Q dot Cv is 0, W dot Cv is also 0. So basically then your control volume will be whatever heat is lost or whatever, I mean, let me just write this way, m dot 1 h1 plus m dot c, I can write this way, m dot c. The air is hot, right? So it is losing its heat or the energy. So it will be m dot 3 h3, and the whatever amount of heat is lost by the air, that is gained by the water. So m dot 2 h2 minus m dot 4 h4. So here m dot 1 is equal to m dot 3 is equal to 2 kilogram per second. M dot 2 and M dot 4 are same since it's a steady state, and that is 0.5 kg per second. Now H1 and H3, H2 and H4. So the cold stream is water, so you can take H as CPT. But for air, it's better to go for this thing, table. Air table will be there. And if you don't have that, you need to do, the thing is, then you have to make one assumption that air is an ideal gas. Because the pressure and the temperature both are changing here. So if you have an ideal gas or air table, you can go there. If not, then you have to assume air as an ideal gas. But in that case, H will be function of, like H will be CPT, right? It will not be function of pressure. So that way also you can do. So basically, I have the values for this question from the table. So, but if you do CPT, let me give you value from air table. Inlet is H1, enthalpy at inlet is 1046.22 kilojoule per kg. But if you just do CPT, CP is 1.005 into temperature, I think 1000 Kelvin. So that will be 1005. So there is difference of 40 kilojoule here. So if you don't have access to the air tables, you can do CPT. If you have, then go for the exact value. That is my advice. So H1 is this, and H3 according to our convention is around 401.3. Here also you can see, if you do 1.005 into 400, you will get 405 or 402. So there is not much difference here, but as the temperature increases, the difference is increasing. So I hope you understand what I am trying to say here. For higher temperatures, this CPT will give slightly higher error in the H value. That is the main point. So anyway, now you have these values, you have mass flow rates. Now coming back, come to this side of the equation. So at the inlet, it is given as the 20 degrees Celsius temperature. So you can take C for water as 4.186 and 20 degrees Celsius, so 293. And if you do that, you should, or again, if you have a steam table, you can take inlet enthalpy as HF of, HF at 20 degrees Celsius. So that way also you can do. And since it's water, it should be matching only. So from steam table, it will be 83.94 kilojoule per kg. And if you do it other way, 4.186 into 293, no, sorry, 4.186 into 20. 4.186 into 20. So it is 83.72. So yeah, if the temperature and pressure are not that high, the CPT also works, but at higher temperature and pressure, it fails. Light gives more error. That is what it is. So now you can find H4, and that will be CPT4, or you can go back to the steam table and see that this H4 corresponds to which HF at T4. So from there you can get T4. So anyway, from both the things, you should get H4 as 2663.62 kilojoule per kg, and the thing is, one more thing is given, the pressure. So P3 and P4 are 200 kilopascal, right? So now you have to see this value should match to HF at 200 kilopascal. Then only it is liquid. So what you can do, you can just check HF at 200 kilopascal, and I have that value 504.86 kilojoule per kg. Hg at 200 kPa is 2706.63 kilojoule per kg. But this value, that H4 we got from the calculation, it is somewhere in between, right? So at the outlet of stream 2, we have two-phase mixture. That is the conclusion. It's not a pure water, pure liquid water. And the temperature will be saturation temperature. So Tsat at 200 kilopascal. So that also you can get from the steam table. So 120.23. So this was the catch in this question. Now the second part. I know we are getting late, but we'll just complete and we'll stop. So again, this is a steady state equation. So you need to write the and this is adiabatic. So on this side only Sgen will be there. And here m dot 2 into, this is for water. So water's entropy increased. So it will be S4 minus S3. And air, which is m dot 1, it entropy decreased, right? So S2 minus S1 will give you negative. This one should be negative and this should be positive, and the total sum should be positive. So now this S4 and S3 you get from the steam table. So m dot 0.5, m dot here is 2, S2 and S1 how will you get? You can use that like 1 second, S2 minus S1. I think I have made a bumper 1 to 3. It is going 1 to 3. So this value will be 3 minus 1, and this will be 2. So this is the correct expression for this our problem. So this one so you'll get from the steam table because it's a two-phase mixture. So you have to do that dryness fraction calculation from here. You'll get x2 as some value. It will be 0.9805. Then you do the calculation and you'll get S4. So this part is clear. For second part, S3 minus S1, how will you get that? So S3 like at the outlet of the airstream, pressure and temperature, and at the inlet also pressure and temperature. So you can assume air as an ideal gas and use that Cp ln T2 by T1 minus R ln P2 by P1. Or I think in that air table also you can get these values, but you have to check the temperature and pressure correctly. There is some relation I think there. So for pressure you can do R ln P2 by P1, but for the temperature term directly you can take the value from that table. So please make that, like, figure out that part. That depends on the book that you are referring, but it will be clearly mentioned there. So if you do this calculation, you should finally get 1.54 kilowatt per Kelvin. So since it's greater than 0, it's a feasible process. So this is I think we'll stop now. This is in a nutshell what this last week's classes taught you, and that's what we discussed. So any one of you have any question, you can ask. I think 2-3 people left already. So Narendra, Priyanka is here. Rishabh is also here. So if you have any queries, you can ask. No queries or nobody is listening. Two possibilities are there. Anyway, so yeah, Narendra, regarding to the assignments, everything is fine?
Everything is in a fine, sir, but there is just small doubt. May I ask there? In the assignment question, hello, sir.
Which assignment? Tell me.
Already I have submitted the assignment. Also, I have that is in a calculated, but just there is a little bit in a misunderstanding in
Which
the
assignment?
this ninth assignment.
Okay. Which question?
Question number 8 in the calculation, determine the pump work input, and there is given the consider the sign of the word done. As per this NA, that answer should be the positive 20.1 kilojoule per kg.
As per?
It is an ask. It is given there. Determine the pump work input. If it is an ask, calculate the pump work, then answer is the negative 20.1. But it is an ask, calculate the pump work input, and also written here the consider the sign of the word done.
So you
As
are
for
saying
me, it should be the plus.
should be positive, you are saying.
Yeah.
Okay. That's not thermodynamics problem. That is English language problem.
Yeah.
I got your point. The question is the language of the question is slightly confusing.
Yeah,
but
yes, sir.
the value is matching, huh? You are getting 20.1.
Yes, sir. Yeah, yes, sir.
Uh, so I think that's better, right? Otherwise,
Yeah.
sometimes the value itself is not matching, right?
Yeah. No, sir, in this assignment, very good questions are in a set.
Uh,
Uh, Very
so
good questions are
uh,
there. Hmm.
I think because of our last complaints, maybe they are giving good questions now. But yeah. Anyway, so other than that, I mean, this is not that big of a. I mean, in competitive exam, you will not get such confusion, and if you get in
Yeah,
that
yeah,
way, you can ask to
yeah,
everyone.
yeah.
So as long as your concept is clear, it's fine.
Yes.
Here it will be somewhat
Yeah,
dubious, but yeah.
thermodynamics is itself a conceptual subject, sir. Every time you have to concentrate, that is anything. You have to think in a lot.
Yeah, yeah.
Yeah,
Like when you do the question, it feels very easy or very
yeah,
trivial. That why are we doing this enthalpy balance every time? But
yeah,
it is a like it depends how much you want to think. You can think.
yeah,
Thermodynamics is like that.
yeah.
So yeah. So anything other than this, Narendra?
Uh, Other things are in a good, no problem.
Any feedback about today's class?
Sir, you have taken actually very good any problems numerical, but
Mm-hmm.
one my views there.
Mm-hmm.
Uh, you take in a just in a simple suppose way. What as per my any view, no doubt you are taking a very good any problem from the beginning. You are
Mm-hmm.
also explaining that is a concept and also giving the idea regarding the competitive exam. Everything is in a fine, sir. But my view is that while giving the problem, instead of giving the data in a directly, you suppose to
Mm-hmm.
give the questions was question statement because in the subject of the thermodynamics, understanding the given in a question that is the main thing. बहुत बार सर इन्हें क्वेश्चन ही समझ में नहीं आता है यानी
Yeah, understood.
my view is that यानी कि instead of giving some of the data यानी directly and better way suppose you will give the statement and from that one suppose you suppose explain for us यानी it will more यानी good. It's यानी my
Mm.
view यानी.
I, yeah, it's a. I mean, the feedback is taken in a constructive manner. Don't worry
Yeah,
about that. Uh,
yeah,
but the thing is, see, if I want to do that way, na, I have to
yeah,
make a presentation PPT file.
yeah, sir. यानी.
Problem in PPT is when you are in presentation mode, you cannot, matlab, like if you
Mm.
write question and then you leave space for writing the answer, na.
Yeah, yes.
But what happens sometimes that space is not sufficient. So that's why I'm doing in this way. But yeah, you are saying I get your point. Maybe
Sir,
what I
even
can
Sir,
maybe.
even in Chakravarti sir,
Mhm.
they also given any more any importance to that understanding of that is a problem.
Yeah, they that
Yeah,
is that is important also.
yeah,
Mm, but what I can do is I can from next time I'll read the question.
yeah. At least any sir, any.
I'll read the complete question first, and
Yeah.
maybe I'll mention which year, which exam it was from,
Hmm.
so that if you want the exact language, maybe you can go back and refer again. But yeah, that is good suggestion actually. I may not realize it, but
Because thermodynamics sir, in understanding the statement that is a very यानी
yeah,
क्योंकि
yeah,
उसके बहुत बार यानी
yeah,
दो दो मीनिंग यानी होते यानी है तो हमारे जो कंसेप्ट यानी सपोज जैसे यानी
yeah. I
मैंने जो
get, I
क्वेश्चन
get.
पूछा है यानी उसमें यानी जो बताया ना यानी तो इट्स यानी समटाइम इट्स डाउटफुल.
I got your point. The next time I'll read the full question first. I'll give you some time to think about it,
Yeah,
and then maybe we can solve it. Cool.
okay sir.
Okay. Priyanka, anything else from your side to add?
No, sir.
Okay. You got today's questions? Like you understood anything?
Yes, sir.
Okay. Narendra, anything else?
Okay, sir. Okay, fine. Okay,
Okay.
thank you very much, sir. Thank you.
Yeah,
Thank you very much.
thank you to all of you also.
Oh,
And that feedback I'll try to incorporate from next time. Okay.
yes. Okay, sir.
Okay. Chalo then we'll stop today.
Oh.
Okay. Bye. Good night.